This course is titled Functional Data Analysis and What to Do When Your Data Are a Curve or Spectra. And the two main instructors are really Ryan Parker and Clay Barker. They're both research statistician developers at JMP. I'm the systems engineer that supports the Defense and Aerospace, so I've been coming to this conference from its predecessors when I worked for the Army about 20 years ago. At that time it was the Army Conference on Applied Statistics, but it's been DataWorks for a while now. And I'm hoping to sort of introduce things, set the stage for this, and then both Ryan and Clay will each have about 2 hours. And then I'm also kind of the buffer at the end with case studies. And so almost everything that I have is recorded somewhere, and I'm providing people a list of all of the recordings and a lot of the content that even Clay and Ryan will present is recorded. You'll notice I'm highlighting a recording that I've watched, but I didn't see it live last year, but there's a research staff member here at IDA, Curtis Miller, who gave a talk on functional data last year. You can certainly, and he just walked in. What timing? Haven't met him, but I wanted to point out that his work's available. I also have highlighted a work here. It's a 10-minute video done by some researchers at the Army's DEVCOM Chemical Biological Center, where they used functional data analysis as the response to a 42-component mixture DOE. I mean, it was really a very big design of experiments to which they used functional data analysis on the analysis side. So all of those recordings are available. I've tried to say, who it is, the length of time, sort of when it was made. And then when you get below that, I sort of have an area here where just, if you searched on some of these topics, I didn't break them out in terms of the detail, but there's close to 50 recordings here. So, this is in the file. You can download it and chase these topics on your own. And so content I don't get to today, I can certainly point you to where you can find a recording of that. The other thing today, we'll try to take a break at roughly about every hour for about 10 minutes. It's not on the actual schedule there. I did also hear there will be snacks at about 3 o'clock this afternoon. So if we need to take a slightly longer break at that point, we can do that. And so let's just point out that these are some of the case studies that I have on some functional data analysis. The first one is using a sensor stream as an input to a machine learning model. I'll probably do that one. The next one is predicting the shape of the sensor stream using design of experiments. I believe Ryan is actually covering that example, so I may not do that one, but I've got a version of it, and again, I've got recordings of both of those. And then I have an example where functional data is used as both the input as well as the output to a model. And so we may be looking at that example at some point later today. So when I look around DoD and say who do I know is already using functional data, it's quite a few people. I moved to the top of the list the video from Curtis Miller here at the Institute for Defense Analyses, as well as the one from DEVCOM CBC. But you can see other places, DEVCOM Armament Center. I know there's some people online. Is everybody in the room from? I know that a lot of people weren't able to travel this year, but they've done a fair amount of work with this. They look at things like gun barrel degradation curves. The Army Evaluation Center, I know they're not here, but they've looked at trajectories, say, of UAVs. Edwards, I only should pronounce it NORCAD, but anyway, that's China Lake. I know they're looking at battery curves, so like voltage versus time or temperature versus time curves to try to predict, whether the batteries are going to be reliable or not. And you can see many of the other organizations on the list that I have talked to most of them are already using functional data. So maybe a quick check in the room. It looks like we're probably about 30 people in the room. How many of you have already used functional data at some point in your careers? Okay, not quite half of the room went up. Okay. And I may want to ask you if you can talk about the kind of data that you have to share that information with us. So I first ran into functional data, it was I think about 18 years ago, and at that time I was an analyst working at the Edgewood Chemical Biological Center, now DEVCOM CBC, and we were doing computer simulations of transport and dispersion of chemical or biological clouds, and looking at maybe 10 factors in that simulation. And at the time, I could model the concentration at a particular time slice, or I could wait for the whole event to finish and sort of model the dosage, total dosage at, at the end of time. But I really couldn't model the shape of that concentration changing over time as the wind is blowing this cloud across the terrain. And at the time, a couple of professors from Georgia Tech were visiting, Professor Jeff Wu and Roshan Joseph. If you know them, they're pretty widely published in the design of experiments and also I think Gaussian process area. But they were talking to me and they said, what you probably need to be using is functional data analysis. But I didn't really have a good tool at the time to do it. So it kind of lingered there for quite a while before I actually found a solution for it. Now, I'm going to give some examples of functional data here. For me, the first ones that I've run into are sensor streams. So if anybody has temperature, pressure, humidity, proximity, vibration, flow, force, intensity, concentration, you probably have a sensor type I don't have listed there, but it's probably recording over time. Okay? So what a lot of people do is they have thresholds, and if it crosses the threshold, the light goes on or the alarm bell goes off. That's what happened in biological detectors. Meanwhile, there could be useful information on how rapidly that curve is rising to the threshold or how much it crosses it. So there's more information than just sort of, that landmark threshold value. How many people have that kind of data? Okay, only one person in the room has sensor data. 2, 3. Okay, don't be afraid to put your hands up. I expected that to be the overwhelming one. The other type of data is when you have data that's taken over a range, things like time, frequency, wavelength, distance, energy, and now we start to get into sort of spectral data. Okay, I actually have the list of them down at the bottom, but let me just take a quick check. How many people do like Raman spectroscopy, NMR, NIR, mass spec, chromatography? Okay, hands are starting to go up. And so spectral data, which can be a lot more complex from my take on it than what you often get with a sensor stream. And it turns out that wavelets really help with that type of analysis. But returning to kind of the list here, so tool wear, gun barrel degradation, I mentioned that, radar, sonar readings, trajectories of flights between cities, landing patterns. I've even seen data from the Army. It was presented at a Moore's Emerging Techniques Forum, where they actually mounted cameras overhead where sort of learning Army surgeons were suturing with synthetic skin. And what they were trying to do was model the movements of their hands to find out what were more effective suturing techniques than not. They could compare them to experienced surgeons versus new surgeons, and so they had all sorts of data plotted over time, which would lend itself to this type of analysis. I think most people have seen electrocardiograms, so that would be another type. So in the end, almost any response in a longitudinal order could be functional data. So I've got just some examples here. There's output from a vibration sensor. Here's some radar and sonar data. This is right off the internet. It probably isn't at all like your real radar data, maybe. Here's aircraft trajectory modeling. So, we've got hundreds of planes and thousands of flights, and we're looking at how their landing patterns are at a particular airport, and we're trying to find, conditions that lead to problems in that path. And so I don't have a grab of a screen from Curtis Miller's presentation, but I think you actually had trajectory modeling in your data set. Yeah, and here we've got 3D space. So the color is the vertical, it's the altitude here. Everything else is latitude and longitude. And this data set, you can find this online. Oh, I think I actually have it around here somewhere. Not that one. These folks, and so their data set is available, and they were using neural network models rather than functional data. So I've wanted to try to apply that to their data set. I haven't yet, but it's a publicly available data set that you can certainly look at to try to do that kind of modeling. The other group that I've lost my slide. This might be it. That did this type of modeling is the French National Aerospace Academy. They've actually modeled the trajectories of flights, say, between Toulouse and Paris. Here's another type of spectra that I ran into. I actually dug out my dissertation because I had a reference to proton-induced X-ray emission. That was 43 years ago, so those of you who'd like to do the math. But what I had were some alloys that I was irradiating and looking at changes in their structure. Well, we manufactured the alloys ourselves. So we mixed our own iron, nickel, phosphorus, boron, made these amorphous alloys. And one of the questions is, how close did we get in our targeted composition? Well, because we had a accelerator there, we could also bring out a proton beam, and you can put anything in front of the proton beam, and it will generate X-rays. And so people do proton-induced X-ray emission. It's a non-destructive test method to try to determine what the composition is. Well, what you get out are spectra that look like this. Here's a peak from the iron, here's a peak from the nickel. So you make some standards, and you get a kind of calibration, what are the set of peaks. Well, we were not doing functional data analysis. I think we could have done a much better job with this type of spectral data. And it's really kind of a cool technique. So one of the examples we actually had was looking for art forgeries. So, if this was a painting here, and I put it in front and I hit the blue, and I'm looking at the X-ray spectra, what I'm looking for is there cobalt or isn't it? Because they weren't using cobalt in pigments until about 1803. So if this is a piece of art they're saying is really from, 1600, and the blue has cobalt, no way. So a very neat non-destructive method. Could have used functional data analysis. Here's one maybe more relevant. You can download this data set from NASA. It's remaining useful life estimation for turbofan engines. So again, we strap sensors on everything. Anybody from Lockheed here? Okay. How many sensors on an F-35? Tons. I once heard, probably 15 years ago, 20,000 sensors. Every time the thing's landing, it's dumping tons of data that go into this something 50, 100 petabyte database. We're recording single thing that's happening on that plane. Well, that's a lot of data over time. That's a lot of sensor data. So this turbofan data would be a set like that. And this just points out that this functional data analysis approach that they used was actually an improvement over some of the neural network approaches that had been done to that point in time. EKGs, most people have seen these kinds of things. I hope you haven't had to see it for yourself for some reason. But you'll notice in the bottom, there's like, oh, what's the distance between these peaks? What's the height of this peak? What's the area under this curve? Okay, those are all what we'll all call landmark analyses, which is often what we've done when we have these sensor stream data. So another talk that was given here back in 2019 at DataWorks was David Harrison from Lockheed Martin, and I actually just pasted his abstract in there. You don't have to read it, so you can't read it. I'll move the next slide. The point is, this is what their data look like. No details on what the data are, except that they had about 30 sensors on missiles that they started building in the 80s, and they're still making. So they want to compare performance over decades. And so, of course, he couldn't share the data with me, but this analysis was done with Lockheed, another vendor, the Navy, and Johns Hopkins Applied Physics Lab. A bunch of people for a week got together and analyzed. So just think how much money that is for that many people in 1 week to analyze. And all they were really doing at the time was, what information can we find out about peak 1 or peak 2 or slope 1 or slope 2 or this delay? And we call that landmark analysis. And they're not using all the data. And so they had kind of an okay answer, but right about that time, functional data became available in JMP, and that's what David used and was able to get much better performance. Since then, I've actually seen the analysis. Joe Warfield from Johns Hopkins Applied Physics Lab, I think he's our closing speaker here this week. But he was able to show me how, he could actually take, there was a sort of a designed experiment over the change in these missiles over the years, and show that if you change this variable, this peak will go up or this peak will go down. So I mean, the ability to predict what's going on in that kind of data was really improved using functional data analysis. So let me just pause there for a second. I've tried to put a bunch of ideas out there so you can go, well, I kind of got that, or that's sort of what I do. Does anybody have a type of functional data that I didn't kind of hint at, that you're going, boy, I really would like to know if we could use this approach here? Anybody want to offer up their type of data? Yes.
So I'm encountering this in applications where one of the data streams I'm probably going to be looking at is basically on or off, right? Or do I see it, do I not see it? So you can imagine that there's a curve where it's like sometimes it's one, sometimes it's zero, but it's one of those two numbers. But I can think of, I found some papers that are like talk about how to deal with that kind of binary response, but yet it's a curve, functional data. But if you have any thoughts on that, I'm curious.
Well, I hope Clay and Ryan are listening, because then when they get their chance to speak, they may want to refer back to that one. Certainly, my first reaction to it would be, could it be used as a supplemental variable that is just a binary predictor in addition to the functional part? I would certainly be trying to set it up that way with how I know how to do that, do analysis with functional data in JMP. No guarantee that that's going to work for that, but that would be my attempt. Okay, and again, this idea of functional data analysis, it's been around for a while. I think the first edition of the book on the left is actually 97, so almost 30 years. And there are people that use other tools to use this, source code like R, MATLAB, probably Python. There are, there's code to do those types of things. The examples you're going to see that when I show them are going to be with JMP, because that's who I work for, and I'm not a coder. I mean, this is all for me is point and click. I know that Curtis had a picture similar to this in his presentation, and I think he referred to one of these authors as your advisor. Is it this slide, or is it just in yours?
Oh, it's just in mine. Liz Robot and
Okay.
yeah, those books are pretty good. Well, all those books are pretty good applied, and also I think the same approach can do with functional data. My advisor's book did talk more about the mathematics and things like central limit theorems and so on and so forth. That these books didn't quite touch on it so much. But Ramsey is kind of given credit as being a pioneer. I don't want to say he introduced it, because that's a bold thing to say. But if someone did introduce it, could have been.
Yeah. Well, it certainly has been the books that, not that I've read all of these, but Clay and Ryan, these are some of the other books that they'll reference in their slides. But this is where, at JMP, where do we get these ideas? Well, we get them out of the statistical literature, and occasionally they come up with some new ideas that they publish too. So, all right, it's at this point that if I was given the talk, I would normally get into my version of what is functional data analysis. I'm going to not steal Ryan's thunder. He's going to lead off with that topic area. So I'm going to actually skip ahead and just do kind of one case study example to try to show you the power of functional data analysis, and kind of, then let them come back and sort of fill in the pieces here. So let me get out of this slide deck here. And I may return to it. Again, all the slides are available. Recordings of all of these things are available. And if you ever have a question about where is something, you know, thanks for sending me a list of recordings, but there's 50, Tom. Can you tell me which one does this? I'm happy to try to help you with that. So the example that I want to show, I close some of these. Is in a talk that I gave. Let me just scoot back to the very beginning of the talk to show it to you. And again, there's a recording of this. But it was on reverse engineering formulations. And so, you know, people, first question, how many people have done a mixture experiment or know what a mixture or formulation design of experiments is? This is where you blend things together, and, you know, we want to say if you blend all this stuff together, this is going to be the performance of that blend. Okay? So that was sort of behind this, and what really kind of drove it, there's two case studies. One is a mixture of alcohol blends, and another is a mixture of these mineral formulations. And so I'm going to scoot ahead to those examples without trying to drag you through all of the DOE part of this. Last year I did a short course here on design of experiments with Jim Wisnowski and Brad Jones, and there's a recording of that. So if your eyes aren't already closing, we've got 5 hours of that for you. But we're going to start with, we're doing a mixture designed experiment. So here's an example of a formulation. It's got 5 components: the binder, the plasticizer, a couple of monomers, and a co-binder. And as we vary those blends, we can affect the hardness of this material, which almost can go from feeling like chewing gum at the lowest extreme to a hard hat at the high extreme, depending upon how you blend these things together. Okay, so that's a 5-component mixture formulation. Okay, here's one that I'm betting most of you have done or watched somebody do. You know, they had this cruet, and on the side of it were lines that said, put this much vinegar, put this much water, put this much oil, add a packet of seasoning, shake it up, and you've got salad dressing. Anybody not ever seen this happen in their life? Okay, so no hands went up. Okay, this is actually my mother-in-law's hand volunteering to show how we did this. And the point I want to make is, why the 5-gallon jug? Because it doesn't matter how much. It's the proportions of oil and water and vinegar that affect, hey, how oily is this? How vinegary is this? How, you know, what's the texture? It's the proportions, not the amount that you blend together. Okay? So that's a really simple example, and we often use ternary plots to try to understand mixtures. The reason for a ternary plot is, if you tell me what 2 of the components are, their proportions, the third is automatically determined. It has to be 1 minus the sum of the other 2. And so that's the way a triangular plot works. If you get 2 coordinates, you automatically determine the third coordinate. So when we think about a mixture space, and I have the triangle on the left, we actually think of, let's focus on the blue curve here. So this is 0. This edge is all no water in the blend. And as I move in this direction, it gets more and more and more and more watery until I get all the way to this vertex. It's pure water. Okay? So if you're thinking salad dressing, you're probably thinking, gosh, I really don't want pure water or pure oil or pure vinegar, right? You want something more like the picture on the right, where the nominal mix was 5 parts oil and I think 2 parts vinegar and 1 part water, if I remember the proportions. But the point is that that sort of hexagon is probably going to taste okay or feel okay in my mouth. Okay, so maybe that's a better designed experiment in that constrained region. Okay, that is a very simple mixture DOE. It's got 3 components, and you probably understand what oil, vinegar, and water are. Here's an example. Again, it's the DEVCOM CBC folks, where they were making these paper tickets with cell-free expressions, so they would print these dots on them. And they could take this paper and dunk it in water and look at the dots and look at the functional data curve from those images and determine, is there toxic metal in there? Is it safe to drink? Or they might wipe it on sweat and learn something about cortisol levels and stress. So they're trying to make these paper tickets for something where soldiers in the field could actually do essentially chemical analysis. And so the formulation actually had around 42 components. That's a lot. That's a 42-dimensional hypertriangle, okay? And they did like 1,500 experiments. The beauty is they had a robot that could blend that all together, so they didn't have to, in the lab mix up 1,500 of these things. But you still have to, print the tickets and do the analysis on the curves. So there's a video on their analysis of that I have the link for you there. Okay. So, and I've actually put the links right in the slide deck here. Again, so the bottom one is the example that I just highlighted. And again, my case studies are all highlighted there. And the top few, a lot of what Ryan will cover will be in some of those. The things that Clay will cover are really some of the newer ideas with direct methods in functional data. So at this point, there may not be a video for what he's going to show until they record it here. Okay, so again, at this point, not to steal any thunder from Ryan, I'm going to skip the overview of functional data and go sort of to the end here where I'm going to use it. And there's sort of two ways I'm going to use this. On the left, I'm showing a triangle with dots. Those are different formulations of these three alcohols. And on the right is the spectrum or the spectral output for a particular blend. Okay, so I can build a model that says, you tell me what you want to blend, I'll tell you what the spectra is going to look like. Okay? But there's another way that we can take this, and that is if you give me a spectra and you tell me it's made from these three alcohols, I can also tell you what the formulation is going to be. Okay? And so we're going to look at an example of that where if I have an unknown target blend, how I can sort of reverse engineer what that formulation is. Okay, so somebody actually did all 303 of these blends. They did, I believe in this case it was Raman spectroscopy. So if I say, hey, if I have these 303, where would be the 6 that would give me the most information to support a model? In other words, I want to build a designed experiment that'll allow me to predict in this space. Well, it will pick the 6 on the right. So basically the 3 vertices, which are the pure quartz, orthoclase, and albite, if I've pronounced those correctly. Any geologists here? I guess I'm the resident expert then. And then the other 3 are close to the middles of the edges because the 50-50 blends would be ideally where we'd want to have them, but they didn't take data there. And so those are the 6 that would give us that information. Okay, but if I make the analogy to the salad dressing, maybe I don't want pure orthoclase or pure quartz or pure albite. I'm interested in combinations near this sort of 6-sided region. Okay, once again, I could say, if you take all of the points inside the ranges I'm interested in, you could then find a designed experiment. So the 6 red circles, which kind of are on the perimeter of that 6-sided region, would give us the most information to predict within that space. And the black circled one is the one we're going to try to predict. Okay, again, you can go download these data. And again, when I first saw this data set, they did all 231 of the alcohol blends, every 5%. And I'm thinking, this is overkill. If you're a design of experiments person, you're thinking, I could do that with a lot fewer. So I thought, well, what if I just did the 10% lattice? I could do 66 blends. What if I did the 20% lattice? I could just do 21 blends. And then if I did the 50% lattice, that's the bottom right with the red circles, that's just the 3 pure blends and the 3 binary blends. And it turns out you can do really well even with just the 6 blends. So those are sort of the 2 examples. So let me scoot ahead and actually do one of these. And so just real briefly what I'm going to show you, I'll do this live for you, but I've got these functional relationships. So I've got the spectra, and I've got the 6 training data set. And in the case of the alcohol, pure propanol only has 3 groups of peaks, not 4 groups of peaks. So I can tell that by that group 21 there. And then what I'm going to do is say, well, that target, that black circled one, which is blend 155, if I have the spectra for that, could you tell me what the concentration is? Okay, so again, without getting into the real details here too much, what functional data is going to do is going to break those curves into 2 pieces. A longitudinal part, we call that the shape function, and a function summary, which is often called a functional principal component score, which is sort of the function-to-function variation. And again, Ryan and Clay will go through these in more detail, but that's the key, is breaking it into those 2 pieces of information. Okay, and then what we'll do is what we'll call functional DOE, because one of the problems is when I do the functional data analysis, so when I look at this picture right here, I've got in the yellow box a spectra. And I can change the spectra if I change the settings of FPC1 or FPC2. Here's the problem. FPC1 and FPC2 are not things I blend together. They're not knobs on my control system. But I do blend together, in this case, the butanol, the propanol, the pentanol. So if I build a model where I model FPC1 as a function of the 3 alcohols and I model FPC2 as a function of the 3 alcohols, I can end up with the ability to say, hey, as I change the amount of any of these 3 alcohols, I can actually watch what the spectra is doing, and it's tied to stuff I can control. So it's, in some respects, this is one of the really powerful things about this, is that we can sort of just almost automatically, if you've got the supplemental data for these extra factors, or in particular if you do a designed experiment, we can actually end up fitting the curves, because there's like an intermediate model where we fit the FPC scores as functions of the factors we really can control. So this will be the slide before we do it, but at pure propanol, which is the top of that triangle, I get the spectra in the yellow box, and notice at 1.31 ppm, the value's around 600 counts. It's not even visible on a scale of 0 to 100,000. And that's basically, at pure propanol, there shouldn't be a peak. Well, as I add propanol in, that peak's going to come up. And so in this case, I'm interested in what is the blend at 155. If I give it the spectra, what is the formulation? And in this analysis, it came up with 44.3, 10.4, and 45.3, and the actual was 45, 10, and 45. So not too far off. In the example of the mineral one that I'll do live, it'll actually even perform better than that. So let me scoot ahead to that example and do it live. Maybe let me just pause here, since I just want to say, well, how might people use this? So people in the chemical, biopharma, food, consumer products, what they might want to do is run a designed experiment with components and factor ranges you believe encompass the unknown competitor's formulation settings. Okay? So I want to make Kentucky Fried Chicken or Coca-Cola, or something that everybody works, this is our secret formula. Well, if I blend enough things together and I take spectra of those products, I can actually start to find out what would be the settings that would let me reproduce that product. Okay? Where might that work in the defense and aerospace? You could help, at one point I interviewed at a company that make those decoy flares that, a plane or a helicopter ejects, so that if there's a missile chasing it, it chases the flare instead of them, these decoy shaft. Well, they were actually blending different pyrophoric materials together, trying to achieve certain spectra. They wanted it to look like the engine. Okay? So, the flare isn't necessarily the engine. So if you want to blend something together with a particular spectra, this would allow you to do that. The other one that I could imagine is, and I've talked with folks up at the Naval Undersea Warfare Center in the past. I don't know that they've actually done this, but I know they do testing where they have a tank And then they might take different shapes, okay? So this is cylindrical with a conical front, or cylindrical with a parabolic front, or different aspect ratios, or maybe they put a sail on it, maybe they put fins, they move it at different speeds, they move it at different angles, and they're measuring sonar data. Well, if you did a designed experiment of that, you could now say, for this particular sonar data, I think it's this shape, moving at this speed, at this angle. So I don't know that they can get that far with it, but that's what I would hope you could do to enhance information from sonar, radar, and spectra of different sensors, is to get more information, because we're going to use all of the data, not just, is there something there? Okay, so now to the live example. So there's the 303 blends. I'm just going to use those 6, and again, try to target something. So let's do that. Now I think I need my glasses. All right, so there are the 6 blends, but this one right in the middle, so sample 247, it's actually got a proportion of 3.13 for the albite, the 0.348 for the quartz, and 0.339 for the orthoclase. So that's the target sample, okay? And although I've saved the analysis here already, I will show you how I could set this up, but I would go into Analyze, Specialized Modeling, Functional Data Explorer. I want to put these 3 design of experiments factors into the supplementary group. I'm actually measuring this versus lambda, and I'm measuring the counts, and then I've got my sample ID as the ID function. So if I've got that all set up, this is where we begin to do our functional data processing here. So the first thing I want to do is tell it the target. So that 247, what I'm telling JMP right now is, don't use 247 to build the model. That's going to be the target. We're going to try to determine what is the formulation. The other thing is, I'm looking at this spectra, and a lot of this stuff over here, there's really nothing going on. So I might want to clean this up a little bit. So if I filter the X, I might want to say get rid of everything above 1200 in lambda. And now I'm focusing on where there's something informative in the data here. So down below here, I can see here are the 6 formulations that we're going to fit, and there's the 1 formulation that's in the target. Those are the spectra, I should say. And then we have lots of different models in JMP, and they've increased over the functional data came out with JMP 14, and at the time it was just B-splines, P-splines, and Fourier bases. Huge jump in capability with spectral data came with the addition of wavelets. Okay, and that came in JMP 17 about 3 years ago. So if I do a wavelets model for this, and basically I'll let Ryan and Clay talk more about the details. I just tried them all and picked the one that's got the lowest criteria here. We're plotting the Bayesian information criteria, so it's picked this Quaflet 5 wavelet to be the basis function. You can see the red curve really does a good job of falling on top of all the black dots, so we're doing a good job here. It looks like I just have 2 shape functions, okay, so you can see them over here, okay, and the first one makes up 92% of explaining the variability, okay, and so we'll come down here, and I'm going to turn on that functional data analysis, maybe make this a bit bigger, make it so it's pure quartz right now. I'm going to put this at, I know data was collected at 472.9, kind of on that peak, okay? And if I now click Optimize Target, you can see that it's picked this to be 0.313, 0.347, 0.34. So that's pretty close to what I told you it was supposed to be. Well, one way to do it is to actually copy out that curve and go over here and let me look at just case 247, and let's just look at the raw data. So this is the data, and I've now fit a model to the other 6, the 3 vertices and the sort of the 3 in the edges, and I've made a prediction curve. So if I paste that curve right on top of the data, you can see that it's just about connecting all the dots. Okay, so this is, we've now got a model that lets us predict. You tell me any formulation of these three components, I'll tell you that formula, what that spectra is going to look like very, very closely. And I can even reverse engineer a formulation. Okay, that's kind of my introduction without explaining the details too much about behind functional data analysis. I hope that you're looking at that going, boy, if we could apply that to my sonar problem or to my, F-35 sensor problem or to whatever, we could get more information out of it. So I hope that's a good motivation to hang around all day. Any questions or comments at this point on anything? Yes?
How do you quantify the sensitivity? So, obviously it's a fairly good one, but, with what margin?
It's a good question, and I hope Clay and Ryan will pick up on that. I very often, I didn't go into my slides on this too much, but I do try to quantify things. Put it this way. People have asked for actually putting confidence intervals on the functional data profiler. They do not yet exist, and I'll let Clay and Ryan tell you where that is and why or why not doing that. But what I was trying to get to here is I really, because I'm not a statistician, I'm a scientist, and so I'm all about checkpoints. So I want to look at my actual versus predicted, and there the green line is the residuals. And so here are 21 checkpoints. So in other words, these points all in that direction, and then in this direction, and then in this direction, they were not used in the formulation. And so I do an actual versus predicted for all of the points. And, I've highlighted here in red the worst case prediction for that. So for these data sets, I know this is the worst case, and it's really not very bad. But in terms of adding things like confidence intervals to that prediction profiler, it's been requested, and I can't give you an update on that, but maybe Ryan or Clay can do that. Any other questions? Okay, let's get Ryan queued up if we could, Matt, and we'll let him go for, we're going to probably take a break not long after 10, so I'll let him say whether he wants us to take it now or would he rather go like 15, 20 minutes and then take a break. So Ryan, are you there?
I'm here. Can you hear me, Tom?
I can. And did you hear my setup to, do you want to just get right into it or do you want people to take a break?
I think it's probably easier if I just go straight through it. So if you want to go do a quick break now, we can do that. And if that works for you guys, in a programming note, I'll go for like an hour, and then Clay will pick up into lunch, and then a little bit after lunch, and then I'll follow Clay before you, Tom, at the end.
Okay, so it's currently just about 9:45 in the room. That's what it says in the back. Let's go until 9:55. And if you want to grab another cup of coffee out there, and those online at home, thank you for attending as well. But let's take a 10-minute break, and we'll get going at 5 of.
Tom, if there are any questions in the audience, if you're able to repeat them, we couldn't really hear what is being said by audience members. And at any point, if anyone has questions, whether you're on Zoom or in person, feel free to interrupt me. I have no problems with that. Happy to just try to answer what I can. And then there was a question, I think, at the end of the session about confidence intervals and the techniques we currently have that we could actually provide. Those confidence intervals don't really provide the right coverage. So currently we're not providing anything because we don't think that they would be kind of giving you the right coverage. That's kind of where we're currently at with those. Unless anyone has anything else before I get started. Okay, great. So like Tom said, I'm going to kind of give the start at the very beginning of what functional data is, kind of what tools we've put into JMP to help analyze this data. A lot of credit to Clay for putting in a lot of the work that we have here. So I have some slides similar to what Tom showed. Clay will also have some things. So hopefully by the second or third time you see it, it'll kind of sink in and seem like about half of the in-person audience had not really used functional data yet. So hopefully it starts to click. So really, functional data can come in a variety of forms. We have time series data, sensor streams data, spectra that Clay will get into after my introduction. You can think about, temperatures over the temperature as being like your input scale and different measurements based on that. And our goal at JMP was to try to make it really easy to model and work with a lot of these kind of functional data. So I think Tom showed some of these books. I think these are the kind of three big ones that we have in some ways relied on. So this Ramsey and Silverman book is kind of like the go-to. There are a lot of the techniques that are in there we have implemented in JMP. This semi-parametric regression covers the piece-blind models in particular, and then the waveless models that we have added. This last book has been very helpful with that. And although I'll show JMP and how we use that, I think the best go-to if you don't have JMP is to try to use some of this in R. There's an FDA package from the Ramsey Silverman book, and then there I think is a semi-par package from the Rupert semi-parametric regression book. They're kind of places to kind of get started if you want to kind of analyze functional data outside of JMP. Okay, so just at a high level, we thinking about functional data where we might have something like our input is a time, in this case years, and we have this kind of smooth curve where we're looking at the home price index. But the reality is that our data set comes at some kind of discrete numbers. We don't have a smooth curve. And of course, we're not thinking about just a single point. We really want all of those points to really have that be a function. But it's not just one function. It's this idea that we have a lot of different functions. So in this case, we might have a function of this home price index over year for every state in the country. So in this case, the starting point and the end point perfectly line up. That may not always be the case, but this is still tools that you would use for signal processing and time series in a lot of different areas. So the idea is with functional data is we're trying to use all the information that are contained in these curves by first converting them to by converting these discrete samples that we have into some continuous function. And we can use these continuous functions to decompose the variation of the shapes of these functions to kind of quantify how they're different. And we can use these quantities, these measurements, as input factors into like a machine learning model to understand how things that we can kind of change might impact the shapes of these curves. So I'm going to go through some examples, some different kind of curves that we've encountered to kind of get you thinking through some examples that maybe you might have. So these curves are runs from a designed experiment where we needed to minimize a clarity measurement across a range of temperatures. So in this case, our temperature is the input, and we have this clarity as our measured output. And in this example, we have a set of infrared spectra of gasoline, and it was used to develop an inexpensive tool to measure the octane in gasoline. The green curves are the ones with the high octane, and the red ones were curves with low octane. And so it turns out that the height of the left peak in this data set ended up being critical for predicting this high or low octane level. So here is a microbial growth curve data, and it's a common type of functional data that you might find in biotech industry. And spectral data has really ramped up in the work that I've been doing with clay. This is a Raman spectra, and something that we can now kind of model and work with in JMP and potentially other software. There's also some high performance liquid chromatography data set that has been used heavily in pharma production. So here's a data set where we have chemical reaction kinetic curves of the amount of a pharmaceutical product, its starting material, and two different kinds of impurities over time. This was a design experiment run in a pharmaceutical R&D department, and they wanted to get as much product as early as possible while also minimizing the amount of impurities and the remaining starting material that they needed to remove at a later step. So the product impurity is in the lower left, and it's the most critical compound to minimize as it was the hardest to remove kind of downstream in the process. Here's another data set where we have multiple kind of output sensor streams. This is from a fermentation process in drug manufacturing. So here we have some profiles of an ethanol amount, a temperature, a tank level, and a molasses speed over time. And we were able to use these as inputs to a machine learning model to predict a critical quality attribute. So we were able to kind of analyze these functions, decompose them into some summaries, and we're able to predict kind of like a yield measurement. Okay, so what's the purpose of learning functional data analysis? Kind of one of the best and most useful things is you have some kind of shapes of a curve or a spectra, and you want to be able to interpret them. So we'll take a variety of different shapes, decompose them into some almost summary shapes, and these will give you some insight into kind of what's happening in this process. But as a part of this, you can also get more accurate results. So kind of users that we had worked with, they would commonly just use summaries of their functions, like the maximum or the minimum or medians or some other measurements to try to predict, say, an end yield or some other quantity of interest. And there's only so much information that's pulling out of the shapes of these functions. Whereas with functional data analysis, you're able to turn them into more compact summaries, more kind of efficient summaries of what's kind of driving the different shapes. And so that's where you can get more accurate results. And they're also a lot easier and accessible, kind of if you're not a statistician, but you understand how these processes work, you're able to gain some insight into them and communicate with kind of domain experts. So another kind of thing that you could attack with a functional data analysis is perhaps you have some knobs you can turn and you want to get your shape to behave in a certain way. I have an example later on where we'll show that, but this comes up in a lot of different industries, and a common question is, how can I tune my DOE factors or some other inputs that I can control to get a particular shape over time for this response that I'm measuring? And so what we've done at JMP is made this hopefully pretty seamless and easy to use, where we can use these factors to predict a function based on how we were able to summarize the different shapes. Okay, so this is kind of a standard workflow in a functional data analysis where you start with kind of your data acquisition step. So you'll commonly design and run an experiment and then load that data into JMP or whatever software that you want it to analyze it with. From there, usually you need to do some cleaning up. So we'll go into here and there some different things that we've added, but there may be things you need to standardize the data, or you need to align the data, or there are some features of the data that you need to get rid of that aren't really of interest. You kind of measure them and you need to clean that up. So that's kind of the next step, that we need to kind of clean those up. But this third step is this idea of smoothing the data that you have. So really, you can just think about, okay, we need to take the discrete points that we have, and we need to turn them into a continuous function. Some of the modeling methods out there, like B-splines or some other basis function approach, will commonly do that smoothing step for you. Clay will kind of talk about this more, but if you're using something like wavelets, they're not actually doing smoothing for you. So you'll kind of almost in this kind of data processing step, you'll almost need to smooth it kind of first. That's more of the exception than the rule, except that wavelets turn out to be really, really good models. So something that you need to think about, do I need to smooth my data up front? Or is this idea of modeling, kind of smoothing all in one, able to work for me? And so once we have these kind of models for our functional data, now how do we decompose it? So, I mentioned kind of having these efficient summaries of these functional sensor streams or other data sets. And so we have this kind of idea of a functional PCA, which is very just similar to a traditional PCA where we're kind of getting decomposing the different shapes into kind of some efficient possibly orthogonal features that, depending on the method we use, for the most part, they'll be orthogonal, but we'll point out when they are not. And so once we have these kind of functional principal component summaries, we're able to use those to model, say, an end yield, or even model the shape of these functions based on these DOE factors we have. So we're able to, kind of start from cleanup to smoothing to summarizing them to then finally turning that into something actionable, taking the things that we extracted, almost like a kind of a feature creation step to now predict something of interest. Okay, so the key piece to make this all work, this idea of taking all of the functions that you might have and decomposing them into some summaries, is this functional principal component analysis. And we'll commonly refer to that as FPCA. You might see slides with FPCA, and that's just this functional principal components analysis. So what happens there is we decompose all these curves into shape components, and they're going to almost be like giving you a feature that's like a typical pattern that you see in the curves. And they will have corresponding weights, and those weights will show you how strongly the individual curves are correlated with these shape components. So like the first shape component you get out will kind of be like the most dominant trend. And as you need more of these components, you'll get other little features like, this particular peak in the data, or this particular way that the functions might move either up or down. And so to kind of illustrate this with kind of hopefully a simple example is this time where we have the input as time and we have this intensity measurement. So things we might ask ourselves are, how are these functions differing from each other? So one thing that's common is that they kind of all have this some kind of peak shape. Looks like about 1 per curve. And then they're kind of going to 0 as you get to the start and the end. So they appear to be symmetric around this peak. But one kind of source of variation we see are these peak heights. And there seem to be some horizontal shifts where some peaks are, kind of between -2 and 0, whereas other peaks are somewhere between 0 and 2. So that's kind of where these peaks are located as another source of variation. And then these are also, the colors are giving us an idea about the area under the curve. So the darker reds have more area under the curve, while the bluer ones have a smaller area under the curve. So here is a trellis plot of the data set, so you can kind of see some of these differences. Hopefully a little bit more clearly. It's don't think it's as obvious to see the peak shift, but you can see definitely different peak heights and the kind of the area under the curve coloring. So in a functional data analysis, the first thing that we do is we need to find a model that'll fit these data. So these really don't have kind of noise in them, but a very common model that I think is a good place to start is with a B-spline. And a B-spline is naturally going to do some smoothing for you. And so if you can get away with using something simple like a B-spline, I think it's worth kind of that being your starting point. But the nice thing is now we have a continuous function that represents this data set. Okay, so this slide is showing us a functional principal component analysis. So at the top we have these components, almost like, we have kind of some eigenvalue measurements and giving us an idea of how much variability is this first component kind of explaining in the data set. So with about 3 components, we're able to kind of summarize a lot of the variation in these different, shapes that we have in these different peak data. So at the bottom here, I've labeled kind of what it makes, kind of if you wanted to try to communicate this to someone, kind of what do these shape functions mean? So this first shape component, under it I have labeled as peak height, and this is kind of representing, okay, how high is that peak? So we have the most weight as you get close to kind of that range of -2 to 2. And if you have a, kind of a larger number associated with this component, you might think, okay, that's giving me larger peaks. And if I have a smaller number associated with it, that's where I don't have as large of peaks. And then in the second shape component, that's kind of our peak shift, where if you have, depending on the value of your associated functional principal component score, it's going to tell you, okay, is your peak more towards that -2 to 0 range, or is it more to that 0 to 2 range? And then finally, we have this kind of idea of a peak width. So this last component is giving us some sense of, are they do we have more area under the curve? Are they wider? That kind of thing. But this is one goal in a functional data analysis. When you get to this kind of first step is, can you interpret what these different shape components mean? Okay, so I kind of briefly touched on a functional principal component and kind of what it is, but they're really these weights that we have a mean function, and then we're going to add in a weight that's multiplied by the first shape function, which is in this data set representing that kind of that peak height. And then we're going to add in another weight that's multiplied by the second shape component. And finally, we'll have a final weight, a third weight that's multiplied by the third shape component. And so with this, if we know what these W's are, the idea is that now we can kind of get back to what each individual function is if we choose these W's in the right way. And as a part of the functional PCA process, we get these W's out. So here's kind of in jump what this might look like. So if all these weights are 0, we're just ending up with the mean, the overall mean. For the first kind of weight 1, as you make it larger or smaller, you can see where it is affecting the peak height, like we kind of had expected. And so this second weight is showing you how the peaks can shift kind of in location depending on the second weight. And finally, with the third weight, we're able to see how these are kind of either elongating out or kind of really shrinking the width of these peaks. So with all 3 of these together, we are able to summarize every function in this data set. So here is what kind of the first peak looks like. So we have in the mean, and then this first functional principal component score was a minus 0.1. So we multiplied that by this first shape component, and then we had a minus 0.6 for the second one, and then add that up with a 0.2 for the last one, and we're now able to get back what the model fit was for the first one. So kind of just to kind of take a step back and clarify exactly what's happening here, the functional PCA is performed on the fitted models. So if you have a basis function model, there's kind of this, if you look in the Silverman-Ramsey book, there's an elegant way to turn the coefficients in a basis function model into and do a functional PCA decomposition directly on those coefficients. And now you end up with a basis function model of the same kind that is representing each of the individual shapes. So this was a B-spline to model the overall curve, and now each of these individual ones turns out they're also B-splines, they just have different coefficients. So it's kind of convenient and nice, and makes it kind of how we are able to fit or go from the different shapes back to the original function. But if you did have noise in this data, you wouldn't, be able to fully, it's not trying to fit into that noise. The decomposition is directly on the fitted model. Okay, here's another example with peak 8. So this has a much taller peak than kind of the average function. So you can see, okay, this compared to this first one, it's got a much larger value for this first functional principal component score. It also has a much larger negative value than the second one, suggesting that it should be more shifted to the left, and then slightly larger for the width. So seems to be a little bit narrower in that case. Okay, so the way that, just kind of summarize, so the way that this is working is we have FPC scores that we are able to extract from all the curves or spectra that we may have. And these are going to represent kind of what, in sort of some kind of mathematical sense, kind of a compact way to represent each of these functions and how the shapes vary. So we can see from this table that weights for the first 10 peaks, so these weights or kind of FPC scores, we can use as responses in a DOE analysis, or as features that we want to input to another machine learning model that will help us think about kind of what some kind of final yield or quality measurement is. So by modeling these weights, we're able to build accurate and interpretable models. And so I'm going to go through an example where you can see how the profilers that we have in JMP are going to kind of make that easy. But the main takeaway is there are kind of two main paths at this point. Once you've done this functional data analysis, decompose your functions into these different weights and to shape functions. So the first path is kind of what we think of as kind of a functional DOE. So the idea is that we want to take these weights and we want to predict them. So kind of as previous slide showed, as you change these weights, we're going to that is allowing us to change kind of how the shapes of these peaks. So if we had some DOE factors that we could build a model to that allow us to predict these weights, now we have a way to turn some knobs that we might control to be able to say, okay, that's going to give me now a larger peak or a smaller peak, whatever may be of interest. Or if we need it to be shifted to a certain way, if we build a model to now predict these, we're able to take something that we can control that we know will predict these values, which, they're great, they represent something, but we don't, they don't really have a lot of we don't have direct control over them. And similarly for this last component. So that's kind of the first or one path you can do. Take factors, build models to predict FPC scores to now understand how you can control how shapes might change. The second path is taking these as features, taking these principal component scores as features, and we have some other responsive interest, like the so we might have a final yield total, and we want to maximize that yield. So we feed in each column of these, each vector of these weights to help us predict what this yield is. So it might turn out that large values of weight 1 are going to give us higher yield, whereas smaller values of weight 2 are going to give us a lower yield. So we need to kind of find what's our optimal weights that'll help us predict what that yield is. And then that in turn kind of ties into this idea of this functional DOE is, okay, well, we have some knobs we can turn. How are we going to get these weights to the right way to get the output? So I'm going to go through an example to kind of work us through some of these ideas. So I think Tom briefly mentioned maybe having this example that he didn't go through, but we have this example from a pharmaceutical application where they were making a product and it needed to be milled down to between 70 and 85 nanometers so that it was in kind of in a specification range that they were able to use. The problem, kind of one bottleneck, is that in this process was the milling time. They needed to try to be within this spec region so that these particles were in this range for as long as possible. They didn't want them to be too large or too small for most of as they were running this process. So they had in this application, there was a 4-factor DOE that had percentage of milling beads. There was a power setting on the mill that they were able to control, a flow rate, and also a temperature. So the idea is they wanted to optimize this to get as many beads as they could in this range as fast as possible and then be done. So this is kind of what one profile looked like for one combination of factors. So this green range is representing kind of what this ideal spec limit is. And this curve, took a lot of while to get there, but seemed mostly to be within range. But the idea is that we want to be able to build something like this. So this is kind of, I'm now starting at the end. In a functional data analysis, we have these 4 DOE factors with percentage of beads, the strength measurement, which is kind of the power of the mill, the flow rate, and temperature. And by tying these back into into the variation of the functions, we're able to predict, when will we enter spec limit? How long might we be there? So this is an example of kind of what the final model looks like. So if you increase the beads, you're going to get closer to the spec region, but seems to be not quite early enough, assuming that you held the other two kind of at their average values. If you adjust the strength, you're going to get into the spec region earlier, but it looks like you might end up going out of spec too quickly without, properly optimizing the other factors. So with flow rate, if we're kind of at the minimum value of flow rate, that's when it seems like the path of this curve is starting to stabilize near the end of the trajectory, which is kind of what we want. We're trying to be in the spec region for as long as possible and to get as many of these beads out within that range. And with temperature, as we decrease the temperature, we get to be a little more to the center of the spec region, which is nice. And so we have we have found process settings, kind of we were able to optimize this so that we get into the spec region at just under 10 minutes, and we get into the middle of the spec region by about 12 minutes. And now I'm going to go through kind of the steps with how we were able to get to this point. So this is kind of the final, what you want to have at the end, this tool that allows you to optimize your DOE factors to get this shape profile of interest. Okay, so are there any questions before I kind of continue? Okay, so kind of this workflow that I highlighted earlier, where do we start? So we needed to collect data, and we're able to get those into JMP where we have this batch ID column. So something that you, depending on how you store your data, whether it's in JMP or any other software, every function has to be kind of connected in some way through an identifier. And so we call it an ID column. And in this case, it's the batch column. We have our X input of time and then our Y output of size that we use. So we kind of our functions are over time with our response being this size. And so this is kind of what we might call a stack data format. You can also think about each one of these being in a row. So you could have, batch 2887 all in row 1, and then your time measurement would then be kind of the next, say, 8 columns of the different times. Or your size would be those columns, and then you might have the column names of the time values so that you could say, okay, this was the time, this was the Y, and have them kind of held compactly in that way if you wanted to. And finally, on the right is where we have our 4 DOE factors with the beads and the strength, the flow rate, and the temperature. In this case, they're constant within a batch. It may be that you do not, that may not be the case, and then that's a little more complicated. It's almost like you might run into a situation where you have a functional input that is kind of driving a functional output. And I don't have an example directly for that, but that's kind of where you get into this. You have to do one functional data analysis on your input and then feed that into the functional data analysis on your output and connect them together. So it's a little more complicated, but it is possible to do. So in JMP, we have our functional data explorer and our specialized modeling menu. And this is where we're going to specify those columns that I showed. So we have our output, which is the size, we have our time input, and then this batch identifier. And the way, at least we do this in JMP, we have these supplementary variables. So these DOE factors, they're not used at all kind of in the initial functional PCA, this decomposition that we do. But by specifying them as supplementary variables, they will allow us to carry those on for further analysis kind of later on in this process. So this is kind of the initial view that you get in JMP, where you can see all of the functions that we have, and there may be different things that you might need to clean this up. Thankfully, this is kind of a fairly well-behaved data set. It's not really noisy. It's not super noisy. They're kind of aligned in the right places. But there are some tools that we have that, whether you're in JMP or another software, you need to kind of think through if it's helpful to you. So we have some situations where it's very helpful to filter out what our input scale is. And by doing that, if you use this filter X option, you're able to specify kind of a region of the input space that you want to focus on. It may be that anything after time 15, maybe that doesn't matter. So that would allow you to do that. So there are also a lot of spectral tools that I think are super beneficial if you have spectral data. I think Clay will cover whenever he talks about spectral data. But there are a whole kind of host of tools that we have that other software might have that you might need to apply to your data set. But again, these are kind of well behaved from the start. So we don't really need to do any of this kind of pre-processing. So now we kind of have this kind of the smoothing or modeling step. And in JMP, we have a few different options. This is actually even a little outdated than what Clay will show. I'll just highlight that at kind of the front where we have this direct functional PCA. We now have a few other kind of direct methods where they're almost just kind of working directly on the data themselves without kind of first fitting these other model forms, like I will show. So I think in a lot of cases, it's great to start with B-splines, especially if your data are simple, kind of well-behaved, do have maybe a little bit of noise, would start with B-splines. We have penalized splines if you have a little more complex shapes, and it can be hard to tune the knots. So if you use B-splines, you have to make some decisions about where knots are located. In JMP, we'll lay out some knots for you automatically. You have some tools to move those around. If you're using like R, you can specify specific locations of knots. But if you have kind of shapes that are varying a lot, it can be a challenge to kind of get the knots all in the right place. And that's kind of where I'll skip down to wavelets. That's kind of where wavelets come into play. So if you do have noise, you do need to do some denoising with a Savitsky-Golay filter, something that we have, or some other technique first. Let Clay get into more of that later. But that's if you do have very wide, a lot of peaks in your data, a lot of shape changes, a lot of sharp shape changes, wavelets are kind of going to be one of the best bets there. And we also have a Fourier basis. If you do have this periodic trends in your data that we don't see a ton of, but it is useful for some data sets. So in this case, even though it's perhaps not really needed, we do wavelets to kind of show you kind of what that looks like to get it all kind of wrapped together. So one thing about wavelets is your data have to be on a grid, and JMP on its own is doing that for you. If you're not using JMP, you have to try to make sure your data are first on a grid. So in this modeling process, it fits a wide variety of wavelet functions, and then just presents to you the best one. I think in a lot of cases, what is kind of the best fit tends to work best, or tends to be make the most sense. There are some cases where you may know that I have this particular wavelet type, so you might want to change from the simlet to a different family. And in this case, we're just going to go with the first one that we have. So from there, once we have this model for the functions, this continuous model, now we do the functional PCA and do this decomposition, where we're able to, from the start, kind of get this idea of how much variation is each component explaining in the data. So really, a lot of the change is controlled by this first shape. Just kind of, I guess, to quickly back up. So we have this kind of overall mean function, right? So this would be, if you gave no weight to any of the shape functions, what the function would look like. And if you recall what these functions look like, a lot of them looked very similar to this. So the kind of the mean is explaining a lot of what's going on, or at least kind of that main trend. So after we account for the main trend, what's next? So this first shape function is explaining about 88% of the remaining variation. So it's kind of a negative weight across the whole shape. So if you get larger corresponding functional principal component scores, you'll end up with these functions that are probably going to be shifted down across the range. Whereas if you get smaller values of this, they might go up if they're negative. This second shape is explaining kind of that next chunk of the variation. It seems to be kind of explaining kind of more this tail behavior, kind of at the very end, with some slight weight of kind of what's happening up to about 10 minutes or so. And so this third component explains just a very fraction of an amount. I wouldn't necessarily try to go too deep into trying to interpret what exactly this is giving us, but there is some small amount of information here. Commonly what you'll find when you do have kind of low amounts of variation explained is the FVC scores will likely be very small, since they're not really contributing a lot to the overall shape. And if you use them later on in predictive models, they may not really be popping up. It may turn out that to predict some final measurement you have, that these shapes that don't really explain a lot kind of almost fall out naturally for you. But one thing we can do is we can kind of see, okay, we chose three, kind of by default, it chose three components for us. What happens, if we try to add more components? It's going to kind of fit the data a little better, but we have these, very small changes in variation explained, and, kind of my rule of thumb, and hopefully yours as well, is if you're kind of getting the same result, pick the simpler version of it. So now we'll go back to 4 shape components, go back to 3. Kind of as you get to 2, you can kind of start to see these actual by predicted plots start to spread out some. Oops. And then if you go down to 1, we're really starting to have, that shape component was definitely seemingly helping fit some of these data points well. And then, of course, if you just use the overall mean, you're going to get a lot of spread in, these actual by predicted plots. So this is one way of diagnosing, how many of these do I really need? So we'll just go back to the 3 that we started with. Okay, so let's think through about kind of how this works. So our shape functions, they're the ones that are kind of helping us explain how the shapes are varying in time. And with those, we extract functional principal component scores that are giving us some sense of kind of the variation between our different batches. So if we look at batch 2887, we have the underlying mean function plus this 112 times the first shape function minus 8.1 times the second shape function plus 1 times this third shape function to kind of get us a model for what that batch is. So these are really compressing the information that we have into hopefully a small number of components as necessary to explain the variation. And so kind of touched on this earlier, but once we have these numbers, now we want to treat those as if they were a response. And we want to find models for our factors that predict those numbers. Let's see. So now what we could do is we could save these summaries out to a new data table in JMP, or to just build a new, say, data frame in R, and now we have summaries for every one of our functions, along with, well, the FPC summaries, but also these supplementary variables that we passed in at the beginning. Kind of at the time, I mentioned these were just carrying over for later, so we didn't need them to do the whole functional PCA analysis, but now we need them if we want to use them to predict these shapes. So if you're in JMP or whatever you might be using, you're free to use any other part of the software to try to build out a model for predicting these numbers, these functional principal component scores from your DOE factors. So you might use fit model, do a tree, neural network, whatever you might want. And so if you did, say, chose fit model, you would now have to treat each of these FPC scores as a response, and you would have to specify some kind of model for, what your different factors are. So we have some kind of it's like a interaction effects model, and we would try to fit that to each one of these FPC scores. That could be a challenge. So it is time consuming. In JMP, we tried to make it really easy by creating this functional DOE option. So what functional DOE option is doing is kind of underneath, behind the scenes, it's going to treat all of these FPC scores as, a response for effectively a lasso model, a ridge regression model that we have in our generalized regression platform. And it's kind of doing all that buildup for you. In our software, if you specify a model script, it'll use that model for the effects. If you do not specify one, it does a simple kind of main effects plus interactions, and then let kind of the lasso decide, which ones we're going to keep or not. So once we launch that option, we get automatically that profiler that I showed you earlier. Kind of this is the final step now where we have the ability to change the different factors to see, when do we get into our spec range? How long might we expect to stay there? Are we going to fall out of the spec range? So one other thing you can do is we made it easy for you to kind of change how these models work. So let's say you're not a jump and you fit a model now and you feel like it's not quite giving you the function that you want. You've got to go back in and change, say, some settings about maybe the amount of penalty that's being used in your underlying model, or tune some other aspect. So we try to make that really easy, where you can go through each of these functional principle components, change kind of what features are being used. So we have things like, number of active effects that you can change and see, when things might enter into a model or not. There are some cases where the default model is we are not going to use any features, which doesn't help anyone. You decide, well, that's let me add the first one in and see if it actually makes sense. Usually it does. It's pretty rare, but it could happen in a lasso model that's what ends up happening. So kind of our goal through kind of how we try to analyze this is to make it as easy as possible, to kind of control all the different steps that you might have to go through. But it's definitely possible to do in other software. And that's kind of what I have planned for this first component. I don't know if we have any questions before Clay gets started, or it's a good time for a break, or kind of where you want to go, Tom.
Review some of those and then take a break. All right, I think this microphone's on. So well, I guess I should first say, is there anybody in the room that has a question? Okay, here's James Womack.
I was wondering if you could output the equation, the prediction equation.
Yeah, so you can when we save, we can kind of go through this whenever we do a demo later as well, but you can save the summary. So the step I showed, where let me try to share this again. I lost Zoom when I shared. So if you are, so if you're at this step and you've saved these summaries, there is actually usually some hidden columns here that will be a formula for the mean function, a formula for the component scores. That's kind of the initial, like if you're at this very initial part. There's also, once you're at the end of doing this DOE analysis, kind of under this menu, there's a way to save out the prediction formulas. So now you have it in your data table to use wherever you might need it.
Okay, and I think we can show that at some point. I can jump here. You're certainly welcome to bring it up, Ryan or Clay, whenever you want to as well. Looking at the questions in the chat, Many of them came in during my session, so the only one that's come in during yours, Ryan, why don't we do that one, and I'll try to address the ones offline that have come in. But this is from Andrew. It says, if the functional principal components are interpretable, then that seems similar to the various landmarks Tom showed before. If you then use functional DOE to predict the weights of the FPCs, then that seems similar to building a meta model for each landmark. So why is doing the former better than doing the latter?
So Tom, I don't know if you can help answer this. I'm not super familiar with the landmark model.
Okay, so when I talked about landmarks before, it would be if you had a curve, and let's say it's got 2 peaks in it. People might just model the peak values, or they might model area under that part of the curve. They might do some statistical summary of just a subset of the data, as opposed to using the whole curve to make the prediction. That to me is the main reason, that is if you can get a better prediction when you use the whole curve. I think that, for me, it's all about checkpoints. If I'm not getting any, if I did a landmark analysis and then I did a functional data analysis and I didn't have the ability to predict better, I would agree with you, it doesn't seem to be doing anything. But from what I have seen, you can generally do better if you're using the whole curve.
Yeah, I think so. Something I'll show in the afternoon is kind of very closely tied to peak. This kind of idea of peak summaries and what you can use those for to make predictions, and how you can. Or we had a need within JMP to try to provide that for users. So I think, for one, like, it may be possible that the full shape, depending on what you're trying to predict, isn't helpful. So usually, if you need like the peak location, like that is a very informative of your process, and a functional principal component may not be directly tying to that peak location, that peak height. It's, could be summarizing almost too much. So there is, it can be, I think I can see situations where there are both. There are some applications where users have told us, I need to know the location and the height of this peak. It is explaining this thing to me. If you do a functional PCA, it's not really honing in on this one thing that I need for the problem that I have. So I think if that is your situation, then it does make a lot of sense to use these specific things that mean something to the problem that you have.
And Ryan, I don't know if we're going to, if you or Clay will do them, but things like the fermentation data set, the anodic bonding data set, where we're doing more of a machine learning, leveraging the functional principal components scores as inputs to a model where we can predict an outcome. I think that would also be a helpful example relative to this question.
Yeah, Tom, I'll show a example kind of like that.
Okay. All right, well, that was the only other question in the chat. Is there any other questions in the room? We're just about, been going for just about an hour solid, so I'm going to suggest we take another 10-minute break right now. And then when we come back, I believe Clay is going to pick up the thread.
That's right.
Okay, so it's 10:51, so at 11:01, we'll resume. All right, folks, it's 11:01, so to keep on track here, we're going to be breaking at noon for lunch for an hour and a half. And just so you know, I saw on the table in the back, there are a list of nearby restaurants, although you can eat in the cafeteria here as well. So you can take a look at the list and make your decision, but we'll have an hour and a half for lunch. And so before Clay gets started here, Carlo Graziani, had a question.
I was just wondering why, among your methods for smoothing and interpolating the data, there was no, it doesn't seem that included in there is some kind of kernel method, like, optimal recovery, radius basis function, Gaussian process, which are also very good at producing sort of smooth interpolations of potentially even of noisy data.
Ryan, do you want to take that one? I know you're more familiar with Gaussian processes than I am.
Yeah, I think we started with basis function models because that's kind of ties you directly into doing the decomposition in a kind of an effective and efficient way. So that those handled a lot of cases until we got to more complex, more complex shapes that something like a Gaussian process may fit really well for. But kind of it turns out I think wavelets are kind of doing that for us. So we haven't kind of gotten to a point yet where we needed to try to now add a new alternative smoothing option, kind of denoising option, if that makes sense. But we're definitely open to, if you feel like, hey, I have data set and none of the stuff that you have is fitting it, but this seems too, can you consider doing that? And we're totally open to that if you have something like that.
And Ryan, one other comment I'd add to that, I think if you're doing Gaussian process, that to me is what we typically do if we've got a completely deterministic process. If it is a noisy process and you do Gaussian process, you are fitting the noise, and do we really want that noise fit? That would be a question I would have. I can tell that Carlo has a response.
I mean, and maybe this is going a bit off the track here, but what a Gaussian process allows you to do is to incorporate that noise naturally, so it produces a smoothing that acknowledges the existence of the noise in a natural way.
Okay, I think we're going to turn it over to Clay to pick up the thread here.
All right, thanks, Tom. I'm just gonna. All right, can you see my screen okay, Tom?
Yeah, we're good.
Okay, cool. All right, I'll just hide this presenter view. All right, we're good to go. So I just wanted to, before I move on with these examples, I wanted to add a bit of a disclaimer. I'm a statistician. I'm not a chemist. So when I look at these pictures here, I just see functions. I don't really know about near infrared spectrometry, which is what I think NIR stands for, or magnetic resonance, which I think is what NMR stands for. In fact, one of the first such data set that I saw was called pork fat Raman spectrometry, which I think people were looking at pork fat from a food safety standpoint. They wanted to look at spectrograms of pork fat to see if they could flag like contaminants in the meat. But when I saw that, because I had no idea what Raman spectrometry was, I thought it said pork fat ramen, which I thought sounded delicious. I thought it was a data set about ramen noodles. So I mentioned that because I apologize in advance if I misspeak about the details of any of these methods. But again, we're sort of looking at them all just as functions. So first, we have mass spectrometry, which we're looking at how the mass to charge ratio changes over time, or whatever the horizontal axis is there. And the peaks in these data are meaningful. So whenever we see a peak in our data, maybe around here, or here, I guess, this represents a protein, and that's meaningful to the scientist that's working with these data. So like the slide say, one of the ways we can use these kind of spectrograms is to compare patients with cancer and without cancer. If we're looking at samples of liver tissue or kidney tissue, or whatever kind of spectrometry. These are also these are chromatograms. So when we dissolve a chemical mixture over time, we want to sort of figure out the relative amounts of the components in those samples. And one example that we'll come back to is identifying olive oils versus other vegetable oils. You can look at chromatograms and use the functional data to predict whether or not it's an olive oil, a vegetable oil, or some other kind of oil blend. And like Ryan alluded to earlier, in the Functional Data Explorer and JMP, we have a variety of ways to look at these. There's B-splines and P-splines, which Ryan touched on, and we'll look at again. You can also do what we call direct FPCA, which is doing essentially like an SVD directly on the data matrix, which we'll come back to after lunch, probably. And then wavelets, which depending on how long we spend on this section, we may get to it before lunch, but maybe after lunch. So we'll just kind of skip over this because we'll spend more time on wavelets later. Okay, so this example is not terribly important, but what I wanted to mention is that we have an unknown row in our data table, right? So this is a row where we don't know the percentage of propanol, butanol, and pentanol, and we want to figure out what function we observed in our data set that's most similar to this unknown function. And we can do that by loading it into the Functional Data Explorer. So if we look at the data, every row in our data set is a function. And we're using this rows as functions format. And we want to load that unknown function as what we call our target function. So we do that using the load target function command, and we're going to pick that unknown target function as our target function. And then we're going to fit a wavelet to do smoothing. And what we want to figure out is using our supplementary variables, can we figure out which of the observed functions is most similar to this unknown function? And we'll do that using the functional DOE analysis that Ryan talked about. And we end up with a profiler like this. So this is what the function looks like depending on the different levels of propanol, butanol, and pentanol. And we can change that. We can change those mixtures and see how the resulting spectra changes. And because we loaded a target function, we can see which combination of propanol, butanol, and pentanol comes closest to our target function. So we can click this optimize target button, and it in the background it solves for the blend of propanol, butanol, and pentanol that gives us the closest combination to our target function. So that's one kind of problem that we can solve using this functional DOE framework, matching a target function like that. Another is we may want to figure out how to resolve these peaks. So if you look here on the left, we have 2 peaks in our data set, but they're really close. And this is called poor separation because there's not much space in between those 2 peak functions. But on the right, this is our ideal scenario. We want a good separation between those 2 peak functions. As you can see, this one is, we can see almost the entirety of the smaller peak, whereas here we only saw a small fraction of it. So this exact same functional DOE framework will allow us to do that peak resolution. So again, we have intensity as our output, and we want to look at that as a function over time for each of our batches. And this time, we're using flow rate and temperature as our supplementary variables. So that's what's going to get loaded into the functional DOE analysis later. So first we get a plot of our data, and again we're going to fit a wavelet, and don't worry, we'll come back in just a little while to talk about what wavelets are. So this is what we get. As you can see here on the right, the actual by predicted plot is quite good. So our wavelets did a really good job reconstructing the original data. And now to focus on a particular peak resolution, we want to filter the range of x's because we only care about a small window here. So we're just going to look between time 22 and 32, right? So we're going to filter down just to that part of the spectra. And now we have a much, this is what was scientifically meaningful in this study. And we want to align those maxima. So there's a processing button here called Align Maximum, and we're going to use that to sort of line up everything so that the maximum is at the same place. So that's what we've done there. And then we're gonna narrow it down again, right? So we've focused in on that one particular maximum, and now we just want an even smaller window there. So we go between -1 and 1, and now we can see that this resolution problem, right? So each spectrogram, we can see there's a big peak and then a smaller peak next to it. This one, they basically have overlapped. So we want to be able to separate them. This one is kind of closer to the ideal. We can see most of the big peak and a little bit of that smaller peak. And we want to figure out what is the combination of our supplementary variables that will give us the best separation between those two peaks. And again, we fit a wavelet in this example, and we're going to do functional data analysis, functional DOE again, because we want to use those supplementary variables that we loaded in to describe these peaks. And now we can see as how does the intensity change as we modify flow rate and temperature. We can sort of play around with those settings until we get better resolution. So when we increase flow rate, that gives us better separation between the two peaks. And when we increase temperature, it also helps separate those two peaks. So really quickly, we were able to fit a wavelet. We were able to sort of zoom in on the part of the spectra that really mattered to us. And then we were able to use our design factors to really help separate those two peaks in our data set. So now I wanted to talk about some pre-processing. So Ryan hinted about pre-processing methods in FDE earlier, and now we'll take a little bit of a closer look. I wanted to mention one of our colleagues and one of our former colleagues wrote a white paper about pre-processing steps for spectroscopic data. They wrote a white paper that's on our website. So if this kind of if this topic sort of catches your interest, there's even more information on our website. And there's also a tutorial where I think Ryan and our colleague Chris Gottwalt talk about pre-processing steps for spectral data as well. So if you look in the Functional Data Explorer, there's kind of a menu of pre-processing methods that are really popular with spectral data. So there's 4 of them. There's the standard normal variate, multivariate scatter correction, the Savitsky-Golay filter, and baseline correction. So what the standard normal variate does is within each function, we're just going to subtract the mean and divide by the standard deviation, right? So it's exactly what you would sort of think it is. When you think about the standard normal distribution, you subtract the mean, you divide by the standard deviation, and that gives you the standard normal. So I think that's probably where this, that's what sort of inspired this name, the standard normal variate. We're just kind of putting everything on the same scale, right? So if what we care about is the shape of the function and how it changes over time, or whatever that that continuous axis is on the horizontal axis, if all we care about is the shape, we can use the standard normal variate to sort of put everything on the same grounds, right? We slide it up or down and scale by the standard deviation. There's also this one called the multiplicative scatter correction. I'm not as familiar with this one. Ryan tells me it's similar to the standard normal variate, but it's specific to correcting light scatter. So I'm guessing it's one of those things where if you have this kind of data, you know what the MSC is and you know to use it. Otherwise, I'm not sure that it's terribly popular. Another one is the Savitsky-Golay filter. And really what that is it uses a moving polynomial to smooth our data. So if you think about putting a window around every point and using a polynomial for prediction, that's exactly what the Savitsky-Golay filter is. Within JMP, we try a couple different window sizes and a couple different degrees for the polynomial, and then we pick the best one for you. But it, regardless of what software you're using, it's easy to sort of fit a simple linear regression or a quadratic and use that for prediction through the range of the data. And we'll take a closer look at this in just a moment. The other nice thing about the Savitsky-Golay filter is that it's polynomials, so the derivatives are really easy, right? So for a linear polynomial, the first derivative is just the slope, right? So it's a really convenient way to get the derivatives of our function as well. So you can use the Savitsky-Golay filter either to smooth your data or to get the derivatives. And we'll look at an example of this in just a moment. I also want to mention there's an option to do baseline correction. And what this is let's say you think that your data really have an exponential decay function as a baseline function. There's an easy way within the Functional Data Explorer to subtract off that kind of baseline function. And we may get to it at the end, but this is something that we're actively working on for the future as well, to add more types of baseline corrections. Okay, so let's take a look. I wanted to take a closer look at a couple of these. So let's take a look at this soil data set. So soil, these are a bunch of soil samples, and we have near infrared spectrometry readings for each sample, right? So if we go into the Functional Data Explorer, we're going to use this rows as function formatting, and we're going to say all of these columns are spectrograms. We're going to load them in that way. Okay, so if we zoom in on these, you can kind of see that the functions are all a very similar shape. They're just kind of slid up and down the vertical axis, right? And let's say that's not very meaningful to our application. We would just want to standardize those so that we could see the overall shape changing. That's kind of exactly what the standard normal variate is meant to do. So we want to go over here to the spectral tab in the Functional Data Explorer, and we want to choose the standard normal variate. So you can see now we've sort of gotten rid of those shifts up and down, and our functions are all sort of on the same scale at the same starting point. So just to sort of hammer that point home, we can see before we did the smoothing, we have these vertical shifts up and down, but after doing the standard normal variate, they're all sort of on the same playing field. So if we wanted to look for differences in the overall shape, that's really helpful because we don't really care about vertical shifts. Okay. I also wanted to sort of really take a look at what the standard or the Savitsky-Golay filter is. So let's say this is our data. We've got some, we can tell we've got some peaks in here, but our data are also kind of noisy. So we want to get rid of that sort of that noisiness, and we want to use the Savitsky-Golay filter. Well, like I was saying, imagine that we sort of slide through our data one section at a time, fitting polynomials and using those to smooth it. Well, we'll focus on here at x equals 113. So we'll scroll down there. And so this is the point we want to smooth. And again, when we really do the Savitsky-Golay filter, we'll do this for all the x values, but it's kind of helpful to see one x at a time. So we want to smooth out row 113, and we're going to use a window of size 5, right? So we've got 5 points after, we've got 5 points above, and we've got our point 113. So now just think about subsetting your data, right? So that's what a moving window like that does, is we're just sliding through the range of our x values, subsetting the data. So now, like I said, when we're wanting to smooth point 113, with a window of size 5, we've got the 5 previous points, we've got the 5 next points, and we've got the point itself. So from there, we could just look at a scatter plot of the two, and we could fit a mean. We could also fit a simple linear regression, and we could also fit a quadratic, right? So that's exactly what the Savitsky-Golay filter is doing. We've got our point 113. A linear filter, if we think about at 113, the quadratic filter would smooth the value to here, and the constant and the linear filter would smooth it to here. So either way, this point would get kind of dropped down a little bit. And like I said, within JMP, we actually vary that window and the degree of the polynomial and choose it for you. So you don't really have to worry about it. And just, I was having fun making this example. So I wanted to create a different kind of plot of the same idea, right? So if we're looking at smoothing point 46 with a window of width 5, this red zone is where we're fitting, and we can kind of zoom in to see exactly what's happening, right? So oops, I didn't mean to zoom there. Let me try that again. Okay, so we've got our point here, point 46, and if we were to use the quadratic prediction, it would bring us down to here, or the linear or constant filter would bring us down to here. And it's kind of helpful to just see a variety, right? So now if we're over here at x equals 90, and we have a window of width 9, we can zoom in here to see what's happening. And again, we've got our we've got our data point here, which is actually really close to the quadratic. So if we were to use a quadratic filter here, this data point wouldn't really change at all. It would basically stay the same. So let's just see what that looks like in practice. We've got our noisy data. We're going to click the Savitsky-Golay filter button. And for this example, I really just want to smooth it. So we'll click filter. That's what does the smoothing. So now we have a much smoother function. And you'll notice, like I said, we didn't have to choose what degree of the polynomial we wanted. It just sort of took care of that in the background, as well as that window width parameter. So yeah, just think of the Savitsky-Golay as a sliding polynomial smoother, right? So just to see again that our data go from pretty noisy to pretty smooth, and that can be helpful for some of these bigger spectrograms. Yeah, so I just wanted to mention as well, I mentioned derivatives. We can also ask for the first derivative, which is kind of cool. We can look at our data and we can say, oh, we have a peak about here, and then you can just kind of confirm that that's around 0 when we do the Savitsky-Golay filter derivative. So you can do that with the first derivative or the second derivative, because sometimes with these kinds of data, it really is the derivative of the function that you're more interested in than the function itself. Yeah, and like I said, I'm not a chemist, and I try to relate things back to things I know more about. So I know a whole lot more about basketball than chemistry. So I found this example. I actually downloaded the data for every game of Kobe Bryant's career, right? So Kobe Bryant was a famous basketball player who unfortunately passed away. It's probably been 5 years ago now in a helicopter crash. But I downloaded right after he retired from basketball. I downloaded this data set with information about every single game he played in his career. And what I was interested in seeing is, how his performance changed as a function of the game number in the season. So maybe earlier in the season he tends to play better or worse, and then later in the season maybe he's tired and plays a little bit worse, or maybe he really amps it up for the end of the season and plays even better. So I thought it would be cool to look at his performance as a function for each season in his career. So we'll go into FDE, and this time I have the data stored in a tabular format. Earlier we were looking at rows as functions, but now it's the functions are stacked. So I want to look at each season. I want to look, so as a metric, I want to look at his points per shot attempt, right? If I score 20 points in a basketball game, which is way in my past, I don't do that much anymore. But if I score 20 points in a game and I only take 15 shots, that's a whole lot better than scoring 20 points and taking 25 shots, because it's a measure of efficiency, right? So that's what I want to look at as my output as for each season in his career. So here we've got all the data sort of overlaid, and in this bottom pane we have each season. And as you can see, it really is a very noisy data set. There may not be a whole lot of signal there. But that's actually exactly why I wanted to use this data set, because it's really noisy and it's hard to see any kind of trend. So that's what made me think of the Savitsky-Golay filter. So these are not spectral data by any means of the imagination, but I still thought that it would be helpful to use the Savitsky-Golay filter. And as I mentioned earlier, or maybe Ryan mentioned earlier, the Savitsky-Golay filter requires your data to be on a grid. Now, basketball players get hurt, so they may miss some games. They may go to the playoffs. They may play extra games. So every season of his career, he played a different number of games. So when we ask for the Savitsky-Golay filter, it says, hold on, our functions are of different length, and we're kind of going to massage the data for each season and put them on a grid to make it seem like he played the same number of games each season. Now, whether or not that's a great idea for this example, that's a different story. But I just wanted to mention that if your data are different sizes, JMP can take care of that for you. So again, I just want to look at the filter. So now we have something a lot easier to sort of look at and make sense of. We can see that in his first season, it sort of he sort of had some peaks in there, and he leveled off at the end of the season. And you can kind of see a lot of these seasons kind of tail off at the end, which honestly makes a lot of sense. Players have injuries kind of piling up, and at the end of the season, they have, you're in the playoffs, so you're playing against stiffer competition. So it kind of makes sense that a player's efficiency would sort of tend to trail off at the end of the season. So anyway, definitely not spectral data, but I think it's kind of a cool way to look at the Savitsky-Golay filter as well. But that sort of, Tom, that sort of ends my section about pre-processing. Do we want to move into wavelets or wait until after lunch? What do you think is best?
I would keep going. I think
Okay.
we'll just break at noon. So you've got about
At noon?
25 minutes or so.
Okay, perfect.
Are there
Yeah,
questions? At this
that'll.
point? No questions. So
Okay, yeah. So we'll get started with wavelets, and then we'll sort of finish after lunch, probably. Okay. Okay, so this is a topic a little bit nearer and dear to my heart because I've spent a lot of time working on wavelets and how we've implemented them in JMP. So I'm sort of dating myself. I still like Google. I don't know what everyone else thinks. My kids think that ChatGPT is the only way to go, but I still like to use Google to give me summaries. So if you were to go to Google and ask what is a wavelet, this is what you would see. So it says they're a wave-like oscillation, which is probably why it's called a wavelet, with limited time duration. So it doesn't go on infinitely like some other decompositions. They have a finite duration. They have a zero average value. Okay, so that's what Google has to say. And then this is my overview of Google's overview. A wavelet is kind of like a basis function that can be used to approximate any kind of function. They have peaks and valleys that kind of make them look like waves. They also take positive and negative values, and they act locally. And I really want to hammer home that point. They can really change in small ranges of the data, which I think makes wavelets really unique. And it's one of the reasons why they can fit really complicated data sets, sometimes better than some of the alternatives. So we could spend a lot of time on wavelets, but we're just going to try to sort of introduce them and show how to use them within JMP. And so that's really what our goal is for today. And when we talk about wavelets, sometimes you'll hear people talk about the continuous wavelet transform, and sometimes you'll hear people talk about the discrete wavelet transform. So this continuous wavelet transform. Think about a wave moving through the range of your data. And with the discrete wavelet transform, think about a wave moving through your entire data set, then half of your data set, then a quarter of your data set, and so on. But we'll get more into that. So we're not really going to talk anymore about the continuous wavelet transform. That's a topic for a different day. So we're just going to focus on the discrete wavelet transform. Now, if we were to look at the definition of the discrete wavelet transform, you might see something like this. So if f of x is our observed function, those are, think about rows in our data set, that if f of x is our observed function, we can use this double sum of these djk, those are our wavelet coefficients, and those psi jk, those are our wavelet functions. And that psi is called the mother wavelet function. So earlier, when Ryan was talking, you might have seen the simlet wavelet, the quafflet wavelet. Those are all mother wavelets. So there's different kinds of wavelets that we could work with. But they do share some commonality, right? So if you integrate them over the range of x, the integral is 0. So essentially, for each of them, that just means that the average value is 0, right? So it tends to be positive and negative, and it averages out to 0. They tend to be orthonormal. They have peaks. And there's this concept of vanishing moments, which just means that if you integrate x to the p times the mother wavelet function, that integrates out to 0. So that people that are in signal processing, I think that's a lot more of a meaningful quantity to signal processing folks. But to me, this concept of vanishing moments is a lot like just a complexity measure. More vanishing moments tend to be a bumpier and more complicated function, whereas fewer vanishing moments tend to be a little bit less active, right? And we'll see some examples of that in a little bit. And these are some examples of mother wavelet functions. The most simple one that you'll see is called the Haar wavelet. It's really just a step function. It's -1 for a range of x and 1 for a range of x. And here's what I was saying about vanishing moments. This bi-orthogonal 1.3 and 4.4. 4.4 has more vanishing moments, and you'll notice it's a little bit bumpier. And likewise, the simlet 4 is a little bit of a simpler shape than the simlet 20. So you don't really need to worry about vanishing moments so much. I've gotten pretty far into using wavelets without really understanding or needing to know that concept well. But really, it's just, more vanishing moments tends to be a more complicated and flexible mother wavelet. But before we go too far, I just wanted to say wavelets are kind of, it's kind of a deep topic, and I think a lot of times, if you're trained as a statistician, the language in the wavelet literature tends to be a little bit different, and it's easy to sort of get caught up on things that aren't really that important for applying wavelets. So what I really want to focus on today is just that there's different wavelets. When we do a wavelet decomposition, we get coefficients. We call those wavelet coefficients. Bigger wavelet coefficients means bigger impact on the shape of your reconstructed function. And then when we do the decomposition to get wavelet coefficients, then we can use a reconstruction method to put them back together into an approximate function. So really, that's what I hope the take home is after we get through these materials, is just that they're easy to use. They lead to wavelet coefficients, and then we use those to approximate the function. And I noticed I noticed that both Ryan and Tom had a slide almost exactly like this. We didn't plan this, but we each apparently recommend 3 books on the topics that we're talking about. But if you're really into, if you get excited about wavelets and you want to learn more about them, these are 3 books that I've found to be really helpful. And kind of like I was saying, wavelets can be a little bit tricky because I feel like the language and the notation is a little bit it's a little bit different from what I was used to seeing. So I would encourage you, if you do end up sort of digging more into wavelets, try a couple resources, because some of them can be a little bit hard to read. But if you look at a variety, it'll start to make sense. In fact, when we first started working on wavelets, one of the first papers I found was called, the title was literally a friendly introduction to wavelets. And I started reading it and I just thought, oh no, this is not friendly. This is not going to go super well. But the more the more you read about these, the easier it gets. And these are definitely 3 good resources. So when we looked at this definition of the wavelet transform earlier, you might have said, well, that looks really confusing. And it kind of is. But I think here I've drawn arrows at what I think is a really key concept with wavelets. We're going to scale the mother wavelet and shift it around. We're going to scale it by a factor of 2. So that's why I mentioned earlier, think of applying that mother wavelet function to the entirety of your data, right? Across the entire range of your data. And then split your data in half and apply the mother wavelet to the left and to the right. And then you just keep going, dividing the data in half until you just run out of data. And I find it helpful to look at graphs of this. So when we talk about the resolution 1 HAR wavelet, it's really just a step function, right? And so it looks like this blue line here. And just think of multiplying that by some coefficient. We call it D11, or really it just needs to be D1 because it's the only wavelet coefficient for the first resolution. Think of multiplying that blue function by some number to approximate our data here on the bottom. And that's kind of how you get the first resolution. And then you split your data in half. Think about looking at the left side and applying that same blue function, and then looking at the right side and applying that same blue function. And so that gives you 2 coefficients, so D21 and D22. So you can also sort of think about it as the resolution 2 coefficient on the left and the resolution 2 coefficient on the right. And then, you might have already guessed it, but we're just going to divide the data in half. Now we've got 4 of those blue functions, so we're going to apply it to each section of the data, and so on, right? So each resolution, we keep adding basis functions, and we keep adding coefficients. So with resolution 4, we have 8 wavelet coefficients. You might have noticed with resolution 3, we had 4. So each resolution, we keep doubling the number of coefficients associated with that resolution. And then it's kind of helpful to stack them up, right? So when we talk about low resolution coefficients, they're associated with sort of global behavior, right? So resolution 1, if there's a big resolution 1 wavelet coefficient, that means it's acting on the entire range of your data. Whereas high resolution wavelet coefficients are much more local, right? This green function here is just acting on a small range of data at the very beginning of your function. or this blue one is working on a sort of slightly bigger section of data at the very end of your function. And so one of the things that I find hard with the wavelet literature is that they always sort of talk about the Haar wavelet. And the Haar wavelet is definitely the easiest. And that's why it's a popular example. But it's not always easy to extend to some of the other wavelet functions, which is why I wanted to add this one for the simlet wavelet. So this is the simlet basis function, the simlet with 20 vanishing moments. So you can see it kind of looks like a wave, shockingly, right? It's kind of a wave-like function. And I made one of the resolution, or one of the basis function bold, so it's easier to trace it, right? So it has kind of just a sort of a smooth up and down, and then you can see it for each resolution getting more and more bumpy. But it's the exact same idea. If you fit the simlet 20 basis function and the very first wavelet coefficient is large for resolution 4, that tells you there's a lot of action in this first region of your function, right? Okay, so I made a little example I want to look at, and maybe after we look at that, it would be a good time to break. So if you're familiar with JMP, you know about the profiler. So this isn't a big data set with missing values. It's just a whole bunch of formulas that haven't been filled in yet. So let's look at a simple Haar wavelet, right? So that resolution 0 is kind of like an intercept. And unfortunately here I called it the coarse coefficient. So sometimes you'll see that language interchangeably. There's, in fact, let me put this sort of next to my slides. Okay. Okay. So thinking about this plot here, this coarse coefficient is like our intercept, right? So if this panel here is our reconstructed function, and these panels, resolution 1, this is the resolution 1 coefficient, the resolution 2 coefficients, and then the resolution 3 coefficients here. So I wanted to see, as I change my wavelet coefficients, what happens to our reconstructed function? So as we move this resolution 0 coefficient around, also here I've labeled it the coarse coefficient, it's just shifting our reconstructed function up and down, right? Not terribly meaningful, but think of it like an intercept term. So this is our resolution 1 coefficient. What happens when I increase it? Well, we get this shape that we sort of expected based on the slides we were just looking at, right? But this resolution 1 coefficient, as we increase it, it's changing the way that our reconstructed function behaves over the entire range of the x values. Okay, so now let's look at the resolution 2 coefficients. What happens when I increase that first resolution 2 coefficient? Well, now I'm seeing some activity in the first half of our data, or the first half of our function, which is exactly what we'd expect, right? And what happens when we modify the second resolution 2 coefficient? Well, the second half of our reconstruction function changes. So I think it can be really helpful when trying to understand wavelets, just to think about what those wavelet coefficients really mean and what it means for our fitted reconstructed model. And then lastly, you can kind of see these resolution 3 coefficients. They're just acting on smaller sections. and so on and so on. But I think that can be really helpful. And just to get a feel for the different mother wavelets, I've got this same profiler, a little bit more complicated, but now we can switch over to the simlet mother wavelet, right? So again, this panel here is our reconstructed function. This is our resolution 0 or our coarse wavelet coefficient. And again, it's just like an intercept term. And here's our resolution 1 coefficient. We can see it's acting on the entire range of the data. And then resolution 2, we get this behavior in the mainly in the second half, and then so on and so forth, right? So we can see that by changing our wavelet coefficients, we can really make a lot of different shapes for our function here, right? And that's one of the reasons why wavelets are so powerful, is because using these different mother wavelets, we can really fit a wide variety of types of data, even when we have big peaks like this or big negative peaks. It can really adapt to any kind of shapes. So I hope it was helpful. I hope it was helpful to see how these basis functions work, because really that's sort of the key to using wavelets. It's not the that psi function and dividing by 2 and stuff. Really just think about sprinkling those smaller functions through ranges of the data, and that'll get you pretty far. That's what you really need to know about wavelets. So that might be a good stopping point. If we have any questions about what we've looked at with wavelets so far, we'll continue with wavelets after the lunch break.
Okay, Clay, I don't see any online. I'm looking around the room. Anybody have any questions for Clay so far on wavelets? Charlie, you want to grab a mic?
I noticed you could do functional DOE analysis and you could do wavelet DOE analysis. Maybe you
Yep.
could distinguish between those.
So we'll get that out. I've got a couple slides about that after lunch. That's a great question though, because that's not super clear in the product. But yeah, we'll definitely revisit that, and we'll take a look at using both of them in the afternoon session.
Okay, are there other questions in the room? Okay, I don't see any other questions here. I will just comment, again, this is the first time I've seen Clay present on the wavelet analysis, and I have seen some of the other developers and statisticians talk about it in the past. I would say the overwhelming thing for me is I feel like I've been using it since it came out 3 years ago, and it just basically tries them all and ranks them, and it seems pretty robust. And so I think it's great to understand it further. I really appreciate the breaking it into the half, the quarter, the fourths, etc., and how that gives you such local sort of correction to the data. I definitely have a bigger appreciation of that, but it just seems automatic. So I really appreciate the fact that you guys make it that way.
Yeah, so Tom, we'll get to that after lunch as well.